So good morning, everybody. Today we're very happy to have Javier Roulet with us. So Javier was a PhD student at Princeton University, but he spends most of his time at the Institute. And then he went on to Santa Barbara KITP as a fellow, as a postdoctoral researcher. And then he went to Caltech as a postdoc. And then now he is a KICP fellow at University of Chicago and also affiliated with the Institute. So Javier is an expert in all things gravitational waves, especially gravitational wave data analysis. So today he's going to talk to us about gravitational waves and the origin of black hole binary. So please welcome.
Mark, and well, thank you all for being here and for the opportunity to talk about my work. And yeah, we'll talk about how we can use gravitational waves to learn about the formation of binary black holes. So it's just been 10 years of gravitational detections. This has transformed the field, but also astrophysics and fundamental physics. And so I know you all know this, but we are celebrating 10 years, so I will say it anyways. Yeah, we have proved that directly detected gravitational waves prove that binary black holes do exist and do merge, and made tests of general relativity, the dynamics from field regime. Notably recently some tests of the area theorem. We have multi-messenger sources that with the kilonova of a binary neutron star merger, we proved that gravitational waves travel at the speed of light. They are associated with short gamma ray bursts, kilonovae, they form Clary elements, and with this it was possible to constrain the equation of state of neutron star mergers and even get an independent measurement of the cosmic expansion rate. Now we are in the fourth observing run of LIGO Virgo KAGRA, and you see in blue are the binary black holes detected through gravitational waves. They are already significantly more than the ones in red that are detected by electromagnetic radiation. And they are increasing very fast, and they will keep improving the detectors for the next 50 years or so. So this is one of the most powerful ways we have of studying black holes. And also neutron stars here that we can also detect.
Sorry. What is the x-axis in this plot?
Random.
All right.
So yeah, the y-axis is mass. The x-axis, I guess they sorted them roughly increasing in both ways, but just aesthetic work. Good. So with over 200 events discovered and more releases coming soon within the next year, we can now study the statistics of the population, what is the distribution of masses, spins, redshift, the merger rate. And by comparing this to predictions for the different formation models of these sources, we can try to constrain how binary black holes are formed. And there are multiple channels formed. For the purpose of this talk, I will concentrate mostly on isolated evolution, which is the case where we have a binary star that each star ends up forming a black hole, and that binary black hole merges. In this case, for example, so the stars, these very massive stars expand a lot, so they will interact in some way, say there will be mass transfer, maybe a common envelope evolution phase. And this is because if the stars are far enough apart that these things don't happen, they also emit so few gravitational waves that they don't merge in the edge of the universe. So something more complicated should happen in this way. And effects like tides, mass transfer tend to align the spin in this case. And so that's one prediction from this channel. The spin should be mostly aligned with the orbit. with the possibility of some misalignment because when the supernova explosion happens from the black hole, if this explosion is not symmetric, the black hole gets a kick and then that distorts or tilts the orbital plane, and then the orbit and the spins can become misaligned in this way. But for the most part aligned. The other big family of formation models is dynamical formation, for example, in globular clusters or nuclear clusters, where black holes from independent stars form separately, and they later form a binary via, for example, three-body interactions that they eject the third body, and then the energy that makes the binary bound in this way, and then via subsequent interactions, they can keep becoming tighter. And since in this type of scenario, the two original stars have nothing to do with each other, the spins should be isotropic between each other and also with the orbital angular momentum. So this is some strong predictions that we can test. And a simple way of testing this is via looking at the effective spin, which is a parameter that is the average of the spin components mass weighted and the component aligned with the orbital angular momentum. This parameter, we pick it because it's one of the best measured spin parameters. And then you see if the spins tend to be aligned with the orbital angular momentum, this quantity will be mostly positive. If they are isotropic, then this quantity, the distribution will be symmetric. So this is something we can test. I will show these results that by now are kind of old, but they are very simple, so I will start with this. The first question we can ask is, do binary black holes even spin? And we do measure so that some black holes prefer the measurement prefer that they are spinning, and we can ask the question: is this just because of measurement noise, or are they actually spinning? So the null hypothesis in this case would be everyone is not spinning, and if that was the case, so here in the x-axis I'm plotting the empirical distribution of the mean of the measurement, so the mean of the posterior divided by the standard deviation. So if everyone was actually zero, then you would expect that this quantity would be distributed like a Gaussian. So this is the cumulative of a Gaussian. Clearly this can explain the observations for say 20 out of 30 of the black holes considered here. But roughly a third of them are clearly positive. So this number of sigmas away from zero is too big for it to just happen from measurement noise. Notably, this only happens in the positive side, not in the negative. So there's an excess of positive spins. This already suggests that the distribution is not isotropic, but we have to be a bit more careful because there are also selection effects. Positive aligned spins tend to emit louder gravitational waves, so we can see more of them even if the actual distribution is isotropic. And we can do more detailed and correct analysis and obtain similar conclusions. So this, I'm testing here a model where there's a fraction of negative effective spins, a fraction of positive effective spins. These are the parameters we try to constrain. And if you focus in this panel here, you see that the fraction of positive prefers to be bigger than the fraction of negative. The fraction of negative is consistent with being very small and zero. And this line here is the isotropic. It's not completely ruled out, but it kind of is very.
So how large is the effect that you mentioned that line spins emit stronger gravitational waves?
Good.
By how much?
So that depends on the magnitude of the spins and somewhat on the masses of the binary black holes. So this effect is more pronounced for heavier binary black holes, and this is because then the merger happens in the middle of the detector band. The effect of having positive aligned spins is that there is like a repulsive force, you can think, between the black holes, and this means there are more orbits until they plunge. And so the merger extends to a bit higher frequency. And if this happens where the detector can see it, it's a bigger effect. So if the spins are very big and the mass is in this range, you can get a factor of several, like 3, 4 in the volume. But if the spins are smaller, this effect is more minor, so 10%. And if the merger is of low mass objects, then so the merger frequency is very high and the detector is not so sensitive there, so it's a less conspicuous difference. Any questions? Well, okay, so more positive effect is spins and negative, consistent with non-negative. So from this type of analysis, one would conclude that this prediction is consistent and satisfied, whereas this one is not. Yeah, this so far I've talked about this chi effective, which remember only cares about the components of the spin aligned with the orbit. So what about the spin orientations? And this part is work that has been led by these two grad students. And so okay, in principle, we are now concentrating on the tilt of the spin versus the orbit. And there are several tilt angles we can define. So if there are two black holes, each of them has a tilt with respect to the orbital plane. We will argue that the tilt of the total spin, which is the sum of the two spins, is actually better measured, more informative than the individual tilts. But in principle, so for each of these three, an isotropic distribution would look like flat in the cosine, and aligned is delta function at 1. And the argument is that so how do we measure spin misalignment? Is because if the spins are misaligned with the orbit, then the orbital plane tends to precess, and this leaves an imprint in the amplitude of the gravitational wave that gets modulated as the binary is pointing at us versus away from us. Now imagine
it has no degeneracy with other factors.
There are some degeneracy, for example, it has been argued that it's degenerate with eccentricity, and in general is not such a strong effect, so it's hard to measure as a consequence. It's even degenerate with no precession in that sense. But okay, I will argue that at least in a few cases we can detect this things. Okay, now imagine, so this is just to paint an intuitive picture. Imagine that the data actually shows these modulations. What this means is that the two spins are not aligned, but it could be that either the primary is misaligned or the secondary is misaligned. And if you just look at each of them individually, it could happen, that each of them is separately consistent with being aligned, just not at the same time. And an example to showcase this situation is this recently reported event that you haven't seen this plot before, the angle, so the left thing is the primary black hole, so the more massive one, the right one is the secondary. The angle here is the tilt of the spin of each component with respect to the orbital angular momentum, and the radius is the spin magnitude in dimensionless units. So 1 is maximally spin. And this is a measurement, and you see it's totally non-distinct. This thing could be non-spinning, could be spinning, could be aligned, could be precessing, could be negative. The only thing we know is it's not maximally spinning and aligned. And yeah, this is one of the loudest events we have seen. However, if you look at the total spin angle, so the total spin with respect to the orbit, you see that it really excludes 1, which would be aligned. And how can we understand this? If now you look at the posterior, the joint posterior for the individual tilts, they exclude the situation where both are aligned at the same time. And they could either be separately aligned, but not at the same time. And then this is a kind of effective I was talking about before. See if it's consistent with zero and even positive. And zero here happens if the total spin is tilted 90 degrees. So remember, chi effective is about the in-plane, the aligned components of the spin. So we have now this angle that we argue is more observable than the individual fields, and then we run population inference for the distribution of these parameters. So the model I will describe here is there's a component that is isotropic with some fraction f iso, and the rest is following some normal distribution with some mu and sigma. And okay, I have three flavors. The green is all these parameters are active. And you see, for example, that the best the best solution has this peak at mu small but positive, and this is what the distribution looks like in terms of costed and left. And correspondingly, there's a peak here. The peak, I mean, may or may not be there actually, so it's also consistent with the featureless thing, but this thing came up. And if you additionally impose constraints, like no, I think the mean should be equal to 1 versus I think there should be not any isotropic. You get also similar constraints in these two cases, and the models fit reasonably similarly well. Interestingly, this isotropic fraction is so equal to 1 would be totally isotropic. Is again not mathematically ruled out, but heavily disfavored. And if you also perfect alignment is ruled out. So perfect alignment would mean no isotropic component, mean equal to 1, and sigma equal to 0. So it's the blue at sigma equal to 0, and this is heavily ruled out again. Yeah, there has been related papers also reaching similar conclusions, and the nice thing about this is that we can point better at this event is definitely not aligned. So on an event by event basis, we know where these constraints are coming from. Yeah, I will put some asterisk here. So yeah, isolated evolution explains the prevalence for a positive and effective, but we do require some misalignment. Maybe supernova kicks can do this, but they need to be fairly large. So this is something to look into. And I will just mention another predictions. Conversely, a prediction of isolated evolution is that there should be no black holes in the range between 45 and 110 solar masses. And this is because of the peri-instability supernova process. So normally a heavier star makes a heavier black hole at the end. And this is until the star gets to over 100 and something solar masses, where at the core of that star, the temperature is so hot that the thermal radiation, the tail of the distribution is gamma rays that can now make electron-positron pairs. And then the radiation pressure these photons were providing gets wasted into making these non-relativistic particles. And the pressure drops inside the star, the whole star collapses and then explodes and leaves no remnant behind. So after some point, those stars that would have made a black hole heavier than 45 solar masses explode with no remnant. And then these black holes are never formed from the direct collapse of stars. There is a way of making such black holes in a dynamical channel, which is if instead of coming from the collapse of a star, it comes from the merger of two lighter black holes. Then no problem producing black holes in this mass range. But then you have more predictions that is, okay, any black hole forming this way should have a spin around 0.7, isotropically oriented, and with a mass ratio typically for a 1 to 2, because this one is a product of merging two black holes. And very interestingly, there's a recent work that shows that. So first of all, we do see black holes in this range. So this prediction is not borne out. And the ones we see are consistent with these properties. Yeah, that's an interesting hint in the other direction. And yeah, another still property that's interesting to look at is the eccentricity. So in the isolated channel, these mergers are driven by gravitational waves, and gravitational waves are very efficient in circularizing the orbit. So by the time they merge, eccentricity should be effectively zero. In dynamical formation, you can form binaries in very tight orbits, very eccentric, that merge immediately. And then this is a way of retaining eccentricity in a small fraction of the mergers. And interesting, there have been several claims of events showing signs of eccentricity. I put an asterisk here because these models are still fairly new, and some of the events that show these signs of eccentricity also have some data quality issues, but it's certainly something that is developing and worth paying attention to.
For the isolated evolution, I mean, if it's not surely an isolated binary, it may be a triple system. Are there dynamical effects that could then affect whether it's just circular orbits or, for example, there's
LIGO cosa is something.
exactly
Yes.
other things? I mean, is it as simple to say that you'd always expect circular orbits in the
I
isolated?
think so. Certainly, for example, in LISA, you can see eccentricity. Because you see it early on in the orbit. I think unless it's something really extreme, my expectation is that LIGO cosa will excite the eccentricity just enough for gravitational waves to start to even kick in, and then after that is like an isolated evolution. This is my expectation. Whether in some fine-tuned situations you can keep exciting eccentricity all the way down, I'm not sure. Since you brought that up, one prediction from this triple brought to merger by LIGO cosine oscillations is that the spins should have tilt. The tilt distribution will have a peak at 90 degrees, which is very interesting in light of this thing I was showing, that if you just let the mu of this tilt, it likes a peak close to zero. I mean, it's not necessary at this point, but I'm just pointing this out that maybe in the future this can still be dropped.
One question.
Yes.
What are the expected rates of each? Like, do we have good predictions for how often?
They are mostly all over the place, these rate predictions. I think in particular for the isolated evolution. But yeah, certainly at least these two channels, they can accommodate rates of the order that we are measuring, which are like tens of mergers per gigaparsec cube per year. Yeah, I think dynamical channels tend to produce more on the lower side, isolated more on the higher side.
When you say that mass gap is observed, what is the ratio between mass gap events and non-mass gap events?
So I was off the top of my head, I would say maybe 5 out of 200. But
what
this
is the
is not
prediction?
the astrophysical. So this is the ratio of observations,
Yes.
which is not the ratio of astrophysical, because these heavy mergers are way louder than the lighter ones. So they are overrepresented.
So it's much lower actually.
Yeah.
And what is the prediction from the formation channel?
So again, this
You
depends.
need the second generation to be generated first.
Yes, and this depends heavily on the type of environment. So, for example, because what happens when sure, you need to merge first to make a second generation black hole, but then when this happens, unless the masses are perfectly equal and the spins are low, but in general you get a kick because at the end of the orbit, there is some final burst of gravitational wave emitted in one direction that carries away linear momentum, and the black hole gets a recoil. This black hole can get ejected from the environment and never emerge again. So globular clusters, for example, tend to have low escape velocities, and then the fraction of this thing happening can be lower, versus nuclear star clusters have a way higher escape velocities, and they can be retained more. Yeah, so I think in globular clusters you can make them small, and this depends also very sensitively on the initial spins of the black holes. If the black holes have even small spins, but non-zero, these kicks are much higher.
So when you say it is observed, is it observed like we do see? That's enough to say you have a cross and a tick. On the left side, there should be none. So but there are some, so it's not good. That's the sense. I mean, it's not quantitative, but it's like the rate we expect. If we see something, then the right side gets.
Yeah, I mean, or you need to invoke some weird deviation from the argument I argued, but yeah, if you take it at face value, if you see one, that's ruled out. Okay. And yeah, the rates, I think they are consistent with the equation. But again, yeah, this also relates to the properties of the initial black holes, and it's an interesting problem. Yes. Thank you for the question. Perfect. Now I will change topic a bit to the gravitational wave detection. Here at the IS, we have developed a search pipeline to look for gravitational waves in public LIGO Virgo data. And how do you go on to detect the gravitational waves? So this basically means you have a stream of data which is coming from the detectors, and at every point in time you ask the question, is there a signal here, yes or no? And how do you answer this question? So the detection pipeline basically outputs a ranking statistic that is a function of the data. And it will be a number that hopefully, if there is a signal, the number will be high. If there is no signal, the number will be low. And this is how you tell apart. Exactly how should you compute this number? From a Neyman-Pearson lemma, it tells us that this is a thing we should compute. If you compute this, you are optimal. If you compute, or any monotonic function of this, if you compute something else, you are not optimal. And so it's the likelihood of observing this data under the signal hypothesis divided by the same thing under the noise hypothesis. So this is great because it's a theorem, gives us an aim to go to, but it doesn't, of course, tell us what is this probability. And for knowing what this, you need to know the physics, the astrophysics, and how your detector works. And for the numerator here, see, the question is there a signal? But this signal could have many parameters. So this hypothesis basically is a combination of multiple hypotheses where theta are the parameters of the source, the masses, the speeds of the black hole, where it is in the sky, all these things matter. Yeah, therefore, you should integrate all of these possibilities to compute this numerator. So this integration we do by brute force enumeration for the intrinsic parameters that are the masses and spins of the black holes. And for the extrinsic, we do semi-analytic integration. And this we can do because the dependence of the gravitational waveform on the extrinsic parameters is simpler, it's analytical, and it involves cosines of the angles and this type of things. And yeah, recently one progress we made is that we were able to include higher modes of radiation beyond the quadrupole in this detection statistics. So binary emitting gravitational waves mostly emits in the quadrupole mode, but especially if the masses are unequal, higher modes of radiation also exist that emit. So the quadrupole is at twice the orbital frequency, but there's different LM modes that I will come later. Different LM modes that go at m times the orbital frequency. And yeah, we were able to include this. I will talk about this in a second. And for the noise part, we also were able to identify and mitigate several noise systematics that had not been realized before. And they generally involve behavior of the detector that deviates from stationary Gaussian noise. And we have these new methods to deal with that. So as a result of these efforts, we were able to detect several new events in runs 01 through 03. And this time we are analyzing run 04A, which was recently released. Yeah, I wanted to mention this also in the context of what I was saying about the very instability gap. Because we do add some new, so here in color is the new events we add, and we add new events in this interesting range, and also in previous observing runs we had a few. And yes.
What are the dashed lines in the M1 redshift plot?
Good. Let's see. This one here. So this one here is the merger frequency becoming as
So that's like too low frequency for the detector.
too low frequency for the detector, and this is because the heavier the mass is,
Yes.
the lower the emergency frequency go, and the farther away you are, also it gets redshifted. So this is that. And this one is too faint. So if low mass sources are less bright in gravitational waves, so you can only see them to some distance. Heavier sources you can see up to farther away. And yeah, we put these lines to try to understand why there are no events here, why there are no events here. Why there are no events here, it's interesting.
So basically we're seeing everything we can possibly see, kind of.
What is that an event?
Well,
Like,
yeah, there's, and these are only 2 dimensions of this high dimensional parameter space. So also it's interesting to see, I don't know, we have a void in kind of negative spins. I think this plot here shows the effective spin versus mass, and yeah, there is this void here. So yeah, it's a rich problem.
I mean, is that an event? Like,
This one?
yeah.
Yes. It has a crazy mass. The color here is the probability of being astrophysical. So it's not hands down sure it's a real event, but it's a 70% sure.
You're using the same cutoff for the probability of being astrophysical as LIGO.
Mm-hmm. Yeah.
But astrophysical, you mean like not noise, or what do you mean?
Yeah. So I was saying, okay, this a number, if it's a real, it should be high. If it's not, it should be low. But there's a gray zone in the middle where maybe real, maybe not. Still report them. But when you introduce or include these events in the population analysis I was describing before, you need to take into account the significance of these events and the possibility that they may or may not be real. And even this, this number even depends on what your astrophysical model is. For example, if your astrophysical model says no, black holes with 200 solar masses are crazy, then the p-astre will go to 0 just because.
Another question, sir.
Yeah.
So you say you have 27 events that weren't found by LIGO. And how many were found by LIGO but not by you?
Yeah, there are also a few of those. And there are basically two modes of this thing happening. One is very marginal events that we make the other decision. Sometimes, I don't know, we have different tests for, say, non-Gaussian noise or something, and maybe one of these tests fires and say, okay, no, actually we think this is a glitch. The other end of this failure mode is conversely very loud signals that even show some effects that are not there in the templates we use to search for them. So, for example, spin orbit precession if the spins are misaligned, or things like that. And then we have a signal quality checks where we put the template, we subtract and look for residuals, and if the signal has extra effects, there will be a residual, and we try to design our search to be as, if it doesn't look like the template, I don't want it, and we do reject some events like that. But in this regime, we are less worried because we trust that these loud signals are found by the other pipelines.
Do you remember the number roughly? Just to have an idea. And is it comparable to the 27 or less?
I think no. These things happening is a few. D45. There is another failure model I forgot that or a failure model. So our search doesn't use the data from Virgo because historical reasons, and the other one is we don't look for times where only one detector is operating, and so some of the events that they detect are in these regimes where they actually need Virgo to make the claim or only one detector was operating. So of these there are more than in each.
They get like different plots. I mean, I understand that you can have specific events which you defer.
Mhm.
You call it an event and they don't, and vice versa. But when you do statistics plot, is there any like region in phase space where you disagree about the existence of events?
So I think the way I put this plot here, I mean so once we include this higher order, this is for the search with higher order modes. This is the latest one we did,
okay.
And there is an excess of things appearing here at higher masses and more. I think this one is large mass ratio. Let me. This gives me a segue to this saying why would you expect more things here? How we carry out this higher mode search? And otherwise you would just use the 2-2 mode. LM equal to 2 is the quadrupole, and match filter against the data. You get some peak if there's a signal, and then from this you compute the detection statistic I was talking about. In reality, the gravitational wave is a superposition of modes, and these modes, the coefficients in front of them depend on some angles of observation. Where are you looking at the signal from? But this is an analytically known dependence, and this one is the one that is not analytical. Just have to simulate these parameters, and so this we build a template bank for, and then and we feed them, we match filter to the data, and then since the total waveform is a combination with some coefficients that you can know analytically, instead of doing that before, we do it after filtering the data, and then just by filtering with a few modes, we can compute the total detection statistic with a low computational cost. So note that these extrinsic parameters don't go into the template bank. The template bank is just the intrinsic. And in this way of doing things where we marginalize the likelihood over extrinsic parameters, this turns out to be crucial. We compare here with injections where we put fake events in the data and we analyze with and without the higher modes. We see a great sensitive volume increase, especially for high masses and for unequal masses. Why is this? Because one effect. So why the mass ratio dependence is because these HLM that depend on intrinsic parameters are more excited for unequal masses. So otherwise, you kind of get a symmetry if you rotate by pi and its equal mass, it's kind of the same system, and all M modes are small or vanish in the equal mass. So in general, unequal masses have higher emission of higher modes. And why the mass dependence is because I was saying the heavier black holes merge at lower frequencies, but these higher modes have higher frequencies. So the 2.2 is twice the orbital frequency, but the 3.3 is triple the orbital frequency. The 4.4 is quadruple. And then those higher modes get again in the bucket of sensitivity of the detector, and they comparatively are more important in those cases.
Why are the masses so large in this plot? Is it for some future detector or is?
No, this is actually measured with injections in real data. And
I would think there would be too low frequency, but no.
yeah, but exactly, it's because these higher modes have higher frequency. And then, yeah, and this is why the ratio is so large, because the denominator, which is the 2.2 sensitivity, is very low. Okay. The last thing I will talk about is parameter inference. So after we detect these signals, we want to measure the masses, the speeds, where it's in the sky. The motivation for this are multiple. The most direct one is very multidimensional astrophysics. There's a merger, imagine, of a binary neutron star. There will be an associated kilonova explosion that is transient. So you want to know fast and very well where to point your telescopes. This succeeded spectacularly with gravitational-wave 17817. Then also, as future detectors keep developing, this number of events will be growing exponentially. So you want to be able to do this fast and also robustly, because if not, the error bars will be dominated by your systematic errors. And there's a more speculative application to detection, which is if you can do parameter estimation really fast, then you can do it on the millions of triggers that the pipeline outputs, and you try to include in some way the information from this parameter estimation in the detection statistic. Maybe I'll talk a bit about that. So for some contributions I did in parameter estimation is coordinate system to improve make more amenable the estimation for gravitational resources. So these are the extrinsic parameters of a typical event, and you see these posteriors are bananas, where I emphasize the banana and the plural. The bananas here arise because they actually measure quantities in phenomenologically in these waveforms are things like the amplitude at each detector, the phase of the wave at each detector, and the time of arrival. And this depends through some trigonometric things on the actual physical parameters, but they are non-trivial. So this is why these shapes arise. However, since we know analytical formulas for these things, we can simply promote them to coordinates, and instead of using a rate ascension declination, we can try to use the time of arrival at one detector, time of arrival difference to the other detector, and quantities like this. Let me see if I have a plot here. Okay, this removes these bananas. For the most part, and now this posterior is way more tractable. And the other thing I was mentioning is the plural is there are multiple modes in these posteriors. In fact, generically 16, which arise from non-approximate discrete symmetry. So, for example, gravitational wave detectors are not good at detecting things coming from the top versus from below, or right-handed versus left-handed, things like this. They produce discrete symmetries. And the posterior that are not exact, they are approximate, but they are pretty good in most cases. And I developed a technique where you can fold the posterior. So imagine this is posterior. If you pick your coordinates carefully, then this will be just reflection symmetries. And you can define a folded distribution, which is just the addition of all the modes properly reflected. And generically, this folded distribution will be unimodal and way easier to treat with samplers. And then from this one, in post-processing, you can reconstruct the original one that you want. So, okay, all these things together make this nasty distribution into nice, almost Gaussian thing that it's just the same problem expressed in different coordinates. And yeah, this method has some direct application to it's very general. So I'm now exploring applications to machine learning for parameter estimation. So this technique I'll talk about is called amortized neural posterior estimation. I won't go through the derivation, but typically, but basically, you have a family of distributions. For example, a normalizing flow that takes data in, and you have a neural network that controls, for example, the parameters of a normalizing flow, and you get a distribution out. So you have a function from data to distributions, and you want to train it so that that distribution you get out is the posterior. This training only requires simulated data, not real data. And this means you can do it up front before turning on the detector, and you do it once. And then you reuse this machine for all the events that you see. This is super promising for data analysis applications where you need to run multiple events with no, you amortize the high cost of training over the many times you use this. Why is this training so expensive? What makes gravitational-wave inference difficult? And this is the large size of the space of gravitational waveforms. So if you just count the intrinsic parameters of the simplest signals you can think of, you already get hundreds of thousands of templates. And on top of that, you need to add extrinsic parameters and extra effects like precession and eccentricity and so on. So the space is really large. However, there is a lot of structure to it also. So this is one of the catalogs. And you should notice that all these signals have a very similar structure. So maybe they have different time scales, which doesn't show in this plot, unfortunately, but and some are louder, some are fainter, some happen in different time delays, and so on. But basically, there's a family of few parameters that describes at least approximately all this variety. So, and moreover, we know analytically in advance what these functions are. So, how can we incorporate this in the architecture of the model and not have it learn post-Newtonian theory again from examples? And yeah, how we formalize this is we think of changing the parameters of the source as a transformation group that acts on the space of parameters and also on the space of data. And how it acts on the data, it's something that it's not important, but we understand what it is. So, for example, there's an overall amplitude of the waveform that depends on some of the parameters, an overall phase, an overall time of arrival, and an overall shape, like the rate of chirping, that we know exactly how it relates to parameters. But we can summarize the phenomenology of all this with a simple model that is some amplitude and some coefficients with some basis functions. And the idea is that then this, at least approximately, will describe any signal that we see with very few parameters. And basically, if you have one, imagine you know one waveform and you want to know another waveform, then you can get this new waveform by applying a very simple transformation to your original waveform, which is maybe add a phase to the wave or add an amplitude to the wave. How we can use this structure? So we take the original data. This is 170817, for example. And we fit a reference model of this form here. That you see basically explains the chirping and when it happens and so on. So the idea is that these parameters are very few. Some of them, like the amplitude and phase, we can optimized analytically, so this optimization happens very fast. And we know exactly what they mean, and they capture most of the information. Then we can apply the inverse transformation. I told you from any waveform you can get to another waveform by applying this transformation. So imagine, let's think that we have one master waveform that we can transform to get any other waveform. So we apply the inverse transformation, which is just in the frequency domain, divide out that base fit signal that you have. I will call this operation heterodyning. And this is what you get after you do this exercise. So basically you remove the chirping and you're left with this master waveform, which I call master waveform because, and it's very nondescript, it's just a delta function in time, no matter what the original source was, if it's a neutron star, if it's a black hole, the mass, whatever, the transformed heterodyne data will always look the same. And furthermore,
Losing information using this process?
great. No. So if I just do this operation and I tell you the heterodyne data and I tell you these parameters, you can reconstruct just multipliers. And so no loss of information. But regarding that, now you see that these data are very easy to compress. Now you just discard all this part that doesn't matter, all that part that doesn't matter, and you are left with a very small chunk of time. Or equivalently, if you think in frequency domain, you reduce the frequency resolution a lot. And then there is loss of information, but indeed that's a compression part. You try to lose the information that you don't need. And this is very important because then you will feed this to a neural network that cannot take thousands of things.
But the original dimensionality is not very high either, right? Like, what was the original dimensionality?
So this, for example, binary neutron star was in band of the detectors for 2 minutes, and you need to sample it at 1,000 hertz at least. So yeah, that's as many 100,000 samples. Versus after this compression, it's order 50. Okay, so I'm developing this implementation, which I call Labrador, because it's now easy to train, because we simplify both the representation of the parameters and the representation of the data. Doing this with normalizing flows instead of, for example, Monte Carlo chain is a very powerful representation. We are guaranteed that the samples we get are from the normalizing flow that we know the density. They may or may not be the posterior if it's not well trained, but then you can correct them by reweighting. I will end here. So by now we have 200 binary black holes with O4A. At least the simplest predictions, like everyone should be aligned, everyone should be isotropic, are challenged. There's these events in the mass gap, there's misaligned spins. We introduce this total spin tilt that makes it easier to identify. And there's observed spin and isotropy distribution. Maybe the explanation is that there are multiple channels at play, or there are these nuances of formation channels that these simplest versions of the story I told you are not totally correct. We were able to include higher harmonics in the search. This improved the sensitivity and covered new events. And I'm working on this amortized inference code that will come out soon. And it makes use of optimized representation of the parameters and of the data. Thank you so much.
We have time for a few questions.
So you always assume that you know the likelihood of this kind of analysis?
So yeah, that's a great question. So in this formalism is simulation based, so you don't, in principle, you don't need to. In gravitational waves, we are lucky that the detector behaves well enough, and we understand the models and so on. So we actually can compute the likelihood, and this is useful for example, correcting the machine learning answer and make it match, for example, with this is a nested sampler answer, and I don't know, they are pretty similar, but you see that, for example, here, the correction works. And so for in the developing stage, this is very useful because I can always check the answers. This also provides really strong convergence guarantees. So if you get the posterior or the normalizing flow answer, and you evaluate the posterior on those points, and you do this reweighting, if all the weights are similar to each other, you get effectively a high number of samples, and then this is a super strong guarantee that the thing is working. And if it's not working, then you also can at least tell that it's not working, because some weights will be very large, some weights will, most of the weights will be small, and the effective number of samples that you get out of this is low. So it's a guarantee that it's working when it's working well, and a diagnostic when it's not. And another thing that evaluating the likelihood lets you do is compute the Bayesian evidence of the quantity of interest, and this can tie to the search, because it's a Bayesian evidence. Bayesian evidence is the integral over the parameters of the prior times likelihood, which is what that numerator in the detection statistic I was saying before. And this is the place where the new physics center, if you want to add precession, eccentricity to our search, the module of the search that needs to change is this numerator. We now need to integrate all these extra parameters. So this may be a straightforward way of going that direction.
But you can also compute PFX with the flow, right? Like,
yes.
And avoid the.
Yeah, and this is much faster, because then you don't need to evaluate likelihood. So if you just don't evaluate any likelihoods, you get this posterior in seconds. So it's 1,000 times faster than the other methods. If you reweight to get all these things I just said, then it becomes tens of minutes again. Any more questions?
Right, let's see if I go.